On behalf of Sam, Joe, and I, we want to thank you for this interesting problem of heating steel up to 400 degrees in 2 minutes, although we found that it could not be done. So then we decided to think outside and of the box and think what other metal could heat up in 2 minutes, and we found that copper is a more excellent way to get this done.
So like Mary said, we determined that steel was not going to be a good solution for this, so we had to create a model. And here I have a physical model of our simulated model. This would represent the rod, and is approximately the same size and shape as the rod that's given the problem, 3 centimeters and 10 centimeters, 3 centimeters diameter and 10 centimeters long. But what we had to do is we had to do a heat transfer relation on this. And so we put heat in at the top, and we want it to come out at the bottom. So the heat goes in through the top through conduction. It also will come out of each of these through conduction down to the next one. And at the whole time, it's convectively coming out of the rod as well. So with modeling it, we were able to derive a feasibility of this situation. Is it even possible? And as you can see here, steel doesn't get remotely close to what we need it to do in 2 minutes, whereas copper, it can get there in 30 seconds. The reason for this, and the reason why we picked copper, is because it has a high conductivity, but it still has a high melting point. So we're not too worried about melting the top while heating up the bottom. Joe's going to be able to explain a little bit about how we're able to control the process of copper and avoid overshoot.
Yeah, so we ended up using the same model that Sam just described, and we did a doublet test. Starting at 23, we hit it up to 50, down to 0, and then back to 23. And then using Loop Pro, we fit that data to a first order plus dead time model and got our process dynamic parameters, our process gain, our time constant, and reset time. And then also using Loop Pro, we got some baseline PI controller parameters for our controller gain and also our reset time. And then using Simulink and MATLAB, we simulated this process with the process and the control. And we actually even added a Smith predictor because the Smith predictors are good for processes that have large dead times relative to the time constant. So we added a Smith predictor, and you can see this is the result. We were able to get the temperature of the rod up to 400 in about 2 minutes. And again, our gain on that is 0.999, and our reset time for our PI controller is 18.4 inverse seconds. The reason we chose 0.999 is because doing our stability analysis, we found that the controller was only stable in the range of 0 to 1. So we wanted to be able to get that keep stability, but also get up to temperature.
Now we do realize by switching out steel for copper that we're giving up some advantages that steel has, such as steel doesn't oxidize and that it's not as strong. But with copper, it's so cheap you can just replace it. And it's the most important thing is that you can heat it up in 2 minutes, and so we can all go home. So if you have any questions.
Okay.